everyone! So this week we're going to be learning a new concept, and this concept or mathematical tool is called integration. But first I'd like to explain to you why we actually need this tool. So one of the formulas that you've learned is that the displacement is equal to the velocity multiplied by the time when the velocity is constant. So if we have constant velocity, as pictured in this graph here, we can find the displacement by just taking that velocity and multiplying by the time. Now if you have a bit of a think about that, let's suppose that our velocity was 4 meters a second. After 1 second, how far would you have travelled? Well, the answer is obviously 4 meters, but another way of thinking about this is the area in this curve here. This calculation is equivalent to this height being 4 meters a second multiplied by this time, 1 second, and the area there would be 4 meters. Now if I was to change to say how far have I travelled in 5 seconds, then I could just have a look when my time is equal to 5 seconds. This larger area here shows me how far I have travelled. So if I want to know how far have I travelled between 1 and 5 seconds, well, it would just be this 4-second time interval multiplied by the speed that I had in that time. So the speed being 4 meters a second. Essentially, the displacement is the area underneath this curve. Now we start to have a problem here. What if the velocity is not constant? So in this particular example, as you can see, I started with some sort of velocity, but now I'm accelerating at some sort of constant rate. So I've got my line going upwards here. So I will have some final velocity, and I'm going to call that v in this situation. So v is the final velocity here. Now, if we have a look, I can actually find the distance or the displacement travelled in this situation once again by finding the area. But the easiest way to find the area is to break into two areas. So I've got this area here, so I'm going to call that area 1, and I've got this other area here, area 2. Now you're used to calculating the displacement, and the formula you've probably seen that we can use in this particular case is S is equal to V plus U over 2 times T. Well, let's show that this is actually equivalent to finding those two areas combined, this total area here. So the total area is equal to area 1 plus area 2. Now if we look at our area 1, in this case it is a triangle. And a triangle, the formula is a half the base times the height. So in this case, if we say that we're interested up to the point time equals t, the base will be equal to t. So it's a half the base, which is t. And the height of this triangle is v minus u. And then if we look at area 2 here, that area is simply a rectangle, and the height of the rectangle is u, and the base of the rectangle is t, so the area is simply ut. So if we add those together to get our total area, we have half t v minus u plus ut, and I can actually factorize out the t's and add these together. So in this particular case, I would get, if I factorize out my t, which is equal to t times 1/2 v plus 1/2 u, and if you have a look, that actually rearranges to v plus u over 2 times t. The same formula that we're used to from our constant acceleration kinematics. So if we want to find the total distance travelled under any shape, so let's imagine that my velocity was constantly changing. Let's suppose it was some weird thing like this, and I want to know how far I'd travelled at a particular point. So let's suppose at this time here, I want to know how far have I travelled. Well, what I could do is, if I want to know how far I've travelled in the first little section of time, then all I need to do is kind of find, okay, I've done this velocity at this time, so I could almost say I've got a little rectangle there. That's the amount of distance that I travelled in the first section of time. Then I could look at my next little section of time, and however much area is in that shape is the amount of distance I've travelled in that particular time. And so what I'm really looking to do here is just add up each of these little different spots and multiply them by the small amount of time, which I'll call delta t, along the bottom here. Now if you think about it, this really makes sense, because if I'm at a point where my velocity is higher, then in the same amount of time I'll have, so the same little delta t in here, I'll actually have a greater area. We'll have travelled more distance in that time. So I'm actually just looking to add a whole bunch of very little areas together, and that will give me a really good approximation for the distance that I've travelled. Now if I can actually take the limit where my little delta t here approaches infinitely small, so that approaches 0, then I will have actually, so divided into infinitely many little areas, I will have calculated exactly what my displacement will be. Now this might sound like a crazy idea, but it's actually been well known for hundreds, if not thousands of years now, and it is called integration. So it is a mathematical process where we add together lots of little areas to find the total area under a curve. And that's what we're going to be learning about this week.